Hi, and welcome again to my Physics Online video lecture series. Today's video, we're going to be continuing a little bit of this discussion of the center of mass motion for a system. This is a discussion that I did in a previous short video that I made a couple days ago. But if you're watching this in conjunction with a course, then you should be watching this pretty much immediately after that video. Is mostly just to kind of, in some sense, codify what it is that I did in that previous video via some further examples. So in that other video, I used the PhET simulation, and I had a couple of masses that I collided with each other, both in 1 dimension and 2 dimension, and we tracked what the little center of mass did for each of these collisions. And essentially what we've concluded is that the center of mass velocity doesn't really change unless there's an external to the system force which acts on one or more of the objects in the system. And that was true in 1D, although we didn't have any good way of showing it in 1D. I guess we could have done the 2D simulation with both particles doing a head-on collision. But it's true in 1D. It's true in 2D, and it's true if you have more than 2 particles as well. You could have like 4 particles or 5 or something like that. And as long as none of them interacts with anything outside of those 4 or 5 particles, your momentum should be conserved, your linear momentum should be conserved, and your center of mass velocity should remain constant. So how is it that we might apply that in some various physics contexts? There are maybe 3 very common examples that are used for this, and every one of them, rather than using a collision, is sort of like the reverse of a collision. Alright, so in a collision, usually you have one object moving in one direction, you have another object moving in the other direction. They crash into each other and they either stick together or they bounce off of each other. So there's usually some sort of a crash, boom, and then afterwards one of them maybe is moving off this way and the other one maybe is moving off that way. Okay, but that's not the only kind of interaction you might have. Aside from collisions, there's sort of the reverse collision or the explosion or the break apart. And the best I can use to describe that is kind of via a few sort of examples. Example number 1 would be having, for example, 2 people that just kind of like push off of each other. So maybe we have a couple of ice skaters, and in fact, I discussed this example earlier when I first was discussing momentum conservation. So you got your ice skater, and then you have a second ice skater that's pushing off from the first ice skater. And essentially what happens is if they're initially both stationary on the ice, and then they push off from each other, then their center of mass, which maybe is right here initially, should stay right here. All the forces here are basically internal, and so as long as you don't have substantial friction, this center of mass will remain right here, and basically this skater will go off with some V2, this one maybe with V1, such that M1 times V1 equals M2 times V2, just in opposite directions. So we might put a minus sign and some vector symbols over them. Okay, and I've already kind of discussed that particular problem before. This would be maybe like the break or split apart kind of problem. Okay, number 2 would be more like the explosion, or again, break or split apart. And this is, you have something like, let's say, a rocket or maybe a firework, and the firework kind of like launches into the air. And this dashed line that we draw, what we drew frankly for projectile motions back when we were doing 2D kinematics, would represent the center of mass motion for this rocket. And so the center of mass should land over here, and basically center of mass, we would have that set of equations that essentially says y is 1/2 times g t squared plus v initial y times t with relevant vectors plus y initial, and x is equal to v initial x times time. Okay, so that would be like your center of mass, or what I'm representing with an x in these pictures. It would basically just follow these equations. That's true whether the firework or rocket or whatever goes like as a whole object, or whether somewhere in its motion it breaks into pieces. So, for example, at this location here, this rocket might like crack up and then have one piece and the other piece, and so one of these pieces may end up landing somewhere over here, and the other piece may end up landing somewhere like over here. And if we know the ratio of the two masses and where one of the two lands, then we can figure out where the other one must have landed as well, and given where the breakup occurs. Frankly, without given where the breakup occurs, we could still figure it out, because the center of mass should just follow the same parabolic trajectory. Okay. Number 3 is, again, going with rocket ships. So if you have a space rocket and it has somehow like the little exhaust nozzles here, and it's blasting out exhaust out of these nozzles, what is actually happening to this system? Well, maybe the center of mass for the rocket happens to be here, and that's the rocket including all of the fuel that is sort of stored in the rocket. So, we have like some fuel here that gets burned and blasts out the back end. And so each particle of the fuel has some velocity in this direction. We could call that V fuel or V exhaust, E for exhaust. And that means that the rocket itself is going to have some velocity in the opposite direction, V rocket. And this little center of mass, this guy is going to have more or less a constant velocity once you're in outer space, at least. You're not dealing with gravity acting on the system. It'll have basically a constant value for the velocity at that point. And so we can figure out, among other things, what should the velocity of the space rocket be, or the center of mass for that matter, given that this fuel has some ejection speed. The equation that governs that is, essentially, we again are just using momentum conservation. And so if you have an exhaust speed VE, and you have, let's say, an initial velocity for the rocket and fuel system, as well as an initial mass for both of those, then for this system, you will end up with a final speed of the rocket, minus initial speed of rocket plus whatever fuel happens to be on board of it, is equal to the exhaust speed times the natural log of the mass of the rocket and fuel initially, so initial divided by the mass of the rocket and fuel finally. And this right here being mass of rocket plus fuel initially and finally. So this gives us what is the actual sort of expected speed of the rocket after it's burned through so much of its fuel. Okay, the other thing that we can get out of this is what's called instantaneous thrust. So instantaneous thrust basically says that the mass of the rocket plus any fuel that happens to be on board times its acceleration, in other words, the F equals ma term, if you will, which is equal to mass times delta V over delta T, must be the absolute value of the exhaust velocity times the rate change of the mass for the rocket. Oops. And where this equation comes from is that if you count the rocket and its fuel as a closed system, then the net force on that system is zero. And that means that the rate change of momentum for the whole system must be zero. And as we know, delta P is m times A plus V times delta m over delta T. Or delta P over delta T is this, excuse me. And so basically, we can rearrange this system by saying that this must be zero. We rearrange the system and we insert that this is the exhaust speed relative to the rocket, and you get this equation here for instantaneous thrust. All right, for our little example problem, we've got a 4.8 kilogram rocket which is being shot from the ground with an effective initial velocity. Essentially, that effective initial velocity is akin to saying, I know that when you actually shoot a rocket off, there is thrust from the fuel. That thrust is non-constant, and therefore it actually kind of speeds up for part of its motion and then enters free fall. Instead of figuring out exactly how fast it's going and in what direction and so on, let's just treat it as if instead of knowing that information, we know the information of an equivalent object that's just simply launched from the ground instantaneously with an initial speed and direction, or an initial velocity. Okay. At the apex, it breaks into two pieces. One of the two pieces, the lighter piece, falls straight down. So initially it's at rest after breaking off and it just drops. So where does the other piece land? To solve this problem, what we need to do is figure out where the center of mass should land and where the actual piece lands, and therefore where the third piece must be. For the center of mass, if we were to draw this thing out, we again have a motion like this. And so the center of mass would land somewhere over here. This is how we defined the range when we did range equation. The lighter piece, by the way, falls straight down and therefore is going to fall half of the range away from your launch point. So we can find those two pieces and then use that to figure out the third. The range equation says R should look like V initial squared times the sine of 2 theta divided by G. If we go back to our original problem, this right here would be V initial, this right here would be theta initial, and of course G is 9.8. Thus, we can say that we know where the center of mass is and where this smaller piece is. Center of mass equation says that the center of mass will be located at this place. So we can use this to solve for x2. Plugging in numbers, we get that the heavier piece lands about 258 meters away. That's all.